So welcome everyone to this week's Origins Colloquium. It's a great pleasure to welcome Ted Bergen to give the talk this week. Ted did his undergraduate studies at Villanova before going on to a PhD at University of Massachusetts, which I guess he completed in 1995. He was then at Harvard CFA for a while before joining Michigan as a professor, assistant professor, then associate full professor in 2011. So he's an expert in astrochemistry and studying star and planet formation. And we're going to hear today about interesting thoughts on the composition of planets forming around these stars. So welcome, Ted.
Well, thanks, Jonathan, and lots of familiar names there on the screen. So, greetings to all the friends and people that I hope to meet again someday soon, face to face. So, I want to talk to you about some work that I've been doing with an interdisciplinary team for over a decade now. And it's a combination of astrophysicists and geophysicists. Their names are up there, and planetary scientists as well. And what we're trying to do, we were trying to seek to understand the Earth and the context that the Earth provides for the exoplanet population. And we've reached a stage where we actually are able to communicate much more directly with the exoplanet observational context, and that's what I'll talk to you today in the idea of soot planets and not water worlds, and I will motivate to you why water worlds don't exist, at least not in the way that a good portion of the field is thinking about them. So this is your obligatory exoplanet plot of planet radius versus orbital period, and it's color coded by detected technique, and the size of it has something to do with the mass of the bodies. I want to focus on this population right here, which is the small planet population that's orbiting fairly close to their native star. And again, most of these sources that you're looking at are Kepler targets, so the native star is typically a G star by and large. Um, the work by Fulton, a very seminal paper, showed that there are two peaks in the distribution of these planets. You don't see it in this plot over here, probably because this pays attention to error bars. This plot doth not. And so this is nominally the super Earth population, okay? And then the question is, what is this population here? The naive interpretation would be it's an Earth-like world with a hydrogen envelope that is puffing it up, or a super Earth world that has the hydrogen envelope. But there's a very important paper that came out in, not too long ago by Luke and Powell, where they, sort of curated the radius and mass measurements and picked the sources that had the most uh, precise measurements. And that's what's plotted here. So what we're seeing here again is this is radius, this is mass, and these are the measurements in the dots here. And what they showed is here's our super Earth population, and that line is the line of an Earth-like composition. So where the material has the density of the Earth, that's what's shown over here. So this is the density over the density of the Earth versus the mass of the planets. And they show that, the stuff on this line has a density similar to the Earth. The stuff over here has a lighter component added to it. And again, that lighter component could be hydrogen, but they showed that, hey, presto, if I have planets that are 50% water and 50% iron silicate, uh, they also match this population. And so the radius valley under this construct wouldn't be anything to do with hydrogen atmosphere or hydrogen atmosphere loss, but rather it would have to do with the birth composition of the planets, and it leads to this concept of very, very water rich worlds. So that brings us to the context of the work that our group has been doing, is trying to understand this beautiful planet here and place it in context. So I'm going to walk you through the journey a little bit to understand the Earth. But before we do that, we have to think a little bit about planet formation. And when we're thinking of planet formation for inner disk planets, their mass by and large is dominated by their rocky core. So we have to pay attention to the rocks and not necessarily the gas. So the gas can be an important component, obviously. And so this is the evolution of dust versus time as envisaged by Karen Meach and Sean Raymond in a very nice figure that I parroted. And so here is dust starting out, a tenth of a micron in size, and you get up to Earth-sized bodies, right? So what happens in the disk very early on is that these micron-sized grains coagulate and form what we call pebbles. And in astronomy, pebbles are sort of millimeter-sized bodies, maybe up to centimeter-sized bodies. And that happens in the disk. And we know these pebbles exist because we have those gorgeous ALMA images that show us the emission from this material. And then the magic happens. That is, we don't quite know how you get from pebbles to planetesimals. Although the leading theory that everyone is using these days is something called the streaming instability. So the pebbles get collated probably in some of these rings. You form planetesimals, and then planetary growth proceeds from that point, not by planetesimals growing together. It's more efficient having the planetesimals accrete the small pebbles. And so this is the predominant theory of planet formation today, or at least how you grow the cores, the Earth-like bodies, the super-Earths, the cores of the sub-Neptunes, and so on and so forth. And so this is a line for pebble accretion for an Earth-like population. And then for the Earth, the record from the moon tells us that we entered a different phase where big things were banging into each other. And so the idea is that you get to Mars size, and then you have this big things banging into each other phase called the oligarchic growth phase. But there are other models where you basically get to this essentially directly from pebble accretion. And this line is, direct collapse of a gas giant. Okay, so that's pebble accretion, and you can get some idea of the timing of this from the solar system. That is, we know in the solar system that 100-kilometer sized bodies were present very early on, like 200,000 years after t equals 0. So all those almal disks we're looking at likely have planetesimals inside of them. Okay, so we have the Earth and we have this carbon-based planet that has, all this life on it. And if you look at the amount of carbon that is on the Earth, it's a very tiny amount. And so that was what motivated our team. That is, if you look at the material that was available, the Earth received one carbon atom per 10,000 available. If you want to think about this from the perspective of nitrogen, it's even worse. And of course, for the same issue exists for water. The Earth is also a water poor world. So we're silicate rock with a tiny sprinkling of the stuff that life uses and needs. And so the question we sought to ask is, well, how did this happen? Is this common? And can then we understand something about the Earth to tell us about the exoplanet population? And I think we are indeed getting there. So this is the data that underlies those assumptions in the previous plot. Okay, so again, we're talking about the rocks. So this is carbon normalized to silicon because the Earth is a silicate rock. All right, and so there we have the sun. That's the total inventory. All right, now we know in the interstellar medium that half of the carbon is in solids. All right, and that carbon appears to be in comets. That is 67P in Comet Halley, where we actually have the data of the solid inventory. And you can actually do some remote sensing observations of the uh, cometary solid inventory. And this is not just these two comets. It appears to be within the population of comets that they are refractory carbon rich. That is, they have interstellar dust, uh, carbon material inside of them. There's been a recent analysis of Uranus and Neptune. Instead of saying they're not ice giants, they're actually methane giants because of the supply of this refractory carbon material. And what is this refractory carbon material? Well, our best guess is from meteorites. That's over here. And that carbon is mostly in macromolecular form. And we can have a whole conversation about the origin of that material. But it likely came from the interstellar medium, and it is provided in 100% form to comets. And then when you get to meteorites, these are the comets that are called the non-carbonaceous chondrites. These are the carbonaceous chondrites, and they are carbon depleted. And there is Ryugu and Bennu would also be here. Now, there is evidence in the solar system that the solar system was chemically separated. That is, these meteorites here and these meteorites here were separated at some time. We actually know that time. It's of order of a million years. And it is theorized to somehow relate to Jupiter's formation, although that is uncertain. Okay. All right, so there's a gradient in the carbon content in the solids, and here is the Earth. This is the Earth's mantle minus the core, and if you account for the carbon that could be in the Earth's core, it would actually be the main repository of carbon. This is a very hard upper limit. It is likely much below this. So the Earth is a carbon poor body, and the inner solar system is carbon poor with respect to the outer solar system. So if we were to look at this inventory based upon observations of ices and comets and so on, we would have half the carbon in refractory organics. I'm going to call it soot, although I'll probably slip back and forth. And then you have the carbonaceous ices. So there's the organics, methanol, things like that, and then our more simpler species. Now, this can be very simply understood within the context of sublimation. That is, how what is left to make planets is likely governed by this process because we're in the midplane of the disk where planets are being born that is shielded from radiation, and the temperature sets the composition at some level. So we have our CO down here, CO2, there's water. This is the estimate we have for soot, and we could talk about that. This is uncertain. But this is the number that we came up with by looking at various things in the literature. And there is our silicate there. All right, so if I start out here in the outer part, the core of my Neptune or Uranus would have all this carbon material, and you would accrete the hydrogen envelope on top of that. If I were to move in a little bit further, you would lose the CO. That's all pretty obvious. If I would go to where Jupiter formed, all right, I would lose basically all the ices except for the organics. And Jupiter should have an awful lot of carbon in its core. And if I go to 1 AU, and this is the midplane temperature based upon measurements of disks, essentially the class 2 disks in the population. These are the so-called protoplanetary disks, and this is the temperature of the dust that we're observing. This was made from by ILSA, this figure. And if I go inside of 1 AU, where we're in the stellar heating dominated regime, it's actually, the disk is very cold, and the Earth should have all of this carbon inside of it. It should be essentially a carbon-rich rock with some silicon. We essentially should have a carbon to silicon ratio of 5, but we have a carbon to silicon ratio that is orders of magnitude below that. So we simplified our thought process of all the various things that planets could be comprised of. And in the inner disk, you have our sort of truly refractory materials, our metals and our silicates, and then the volatile components, the soot, the water ice, and hydrogen. And the Earth is formed from those refractories with some soot and some water. And the Earth formed inside the ice line, it's water poor. And under this construct, the Earth must also have formed inside the soot line. And so here is a model that sort of relates that. I have temperature versus radius. This is the radiation dominated regime. That is where nearly all of the protoplanetary disks are dominated by stellar heating by and large. And there is the soot line. All right, so we see the problem. The Earth should be carbon rich. And how do you get around this? Well, if you go to earlier phases where there's accretion heating, the dot should be on top of the M here. We can crack that down by time. You go to earlier phases, there's more energy in the system due to accretion. And you get to very young stages, about a million years, less than a million years, when we know planetesimals were forming, that the soot line can be all the way out into the asteroid belt. And so the idea is here is this: you have your disk here. There I have my carbon grains, my silicon grains. They probably are mixed together. They're probably not separated population. The system is more luminous because of accretion heating, and the inner disk is carbon poor. And I make my planetesimals out of this, and the Earth is constructed out of the planetesimals and whatever pebbles are left. Uh, Essentially, the conditions that led to the formation of the Earth must have been set fairly early. All right, so that's the idea. Of course, there's a problem that the pebbles move in the disk due to the gas pressure gradient. They actually have differential forces, and so they drift inward. So there's this constant supply of carbon-rich material that's kind of hard to get rid of. And the way you do that is the grains are drifting to the pressure maximum, which is the inner edge of the disk. And if I have something such as the formation of a planet, I can reverse the pressure maximum since that there's a pressure edge here. These grains will get trapped out here. These grains will go in, and you make the Earth out of this stuff. Again, all right, that's all good, except for these traps are leaky, as many models show, so that's a complication. And not all systems, of course, have this Jupiter here. And so that suggests that there's an awful lot of planets forming out of carbon-rich pebbles that are drifting in. So this is the idea then. Okay, the Earth formed here, right? But then there's this part here where you have planets that have a lot of carbon, but and silicon, but very little water. And then this part here where I have water, carbon, and silicon. All right, so here we are. This is the Earth, right? Based upon comets, and this is the refractory composition of 67P in percentage of mass. They have an awful lot of carbon, and that's in this macromolecular material. So if I have a planet born here, this would be a soot planet, essentially. Would be rocks like the Earth plus organics. And I go out here, this is our putative water worlds. They form beyond the ice line. They don't, water worlds, 50% silicate, 50% water, do not exist. The solar system tells us this. If you form beyond the ice line, all that carbon in that macromolecular material is still there. And so they would be carbon rich water worlds, soot water worlds, carbonated water worlds, whatever we want to call it. Okay, so there's soot water worlds. So this is our idea of interdisk planet formation. You would have the potential for rocky planets, soot planets, and water worlds. And obviously, there's lots of complexity here. But the role of carbon, I think, will be quite determinative in the observable features of the atmospheres of these various planets. So here are a series of predictions from this model. Prediction one is that soot-rich planets should foster haze production. So what we did is we looked at a model where we had planets that were basically Earth size or less, or Earth mass or less, and one 3-Earth mass planet. They're formed of metals and silicates, and we added some soot by mass. Now, in principle, comets are 28 weight percent by mass. So in this model, we actually reduced it by quite a bit. The Earth, of course, is well below these numbers. It's like 0.001 weight percent or something like that. Now, we assume that this is a soot planet, that it formed with no water, and then we added some water in another model. Now, this is the composition that we estimate for soot. This is the macromolecular material. And so one thing to think about for the perspective of water and planets, the limiting factor for water production is not oxygen, because the silicates have a ton of oxygen. It's hydrogen. All right. And so the soot, it comes with an awful lot of hydrogen. So these planets will not be water zero. They won't have zero water. They will have a decent amount of water because for every 100 carbon atoms, you're providing 77 hydrogens on average. All right, so they're going to make water. All right. And this three Earth mass planet will accrete a hydrogen rich envelope. It'll be a sub Neptune. Okay. Then what we do is we solve for the equilibrium of a molten mantle and the overlying atmosphere. That gives us the composition at the base of the atmosphere, what outgasses from the mantle. And then we solve for the equilibrium chemistry of an atmosphere given a pressure temperature profile, and we predicted the composition at the depth probed by transmission spectroscopy. Okay, so there's caveats here. As I told you, comets are much more carbon rich than in our model. But I think the results, in fact, we now have done the calculation. The results are similar if we use a higher weight percentage and if we go to slightly larger mass planets. Our model is for young planets for a Earth-sized world, and so we're not doing plate tectonics. That's a step next. We have to start looking at that. And the three Earth mass planet is more representative of the existing exoplanet population, and the weight of that hydrogen envelope should lead the mantle essentially to be molten. So it will be communicating and outgassing into the atmosphere. So these are our predictions. The composition here is sampled at 1 bar. This is H2, methane, and a bunch of other species in the atmospheres. This is the percentage composition of which is present in the atmosphere. These are different models for the three Earth mass planet, different amounts of soot, different amounts of water. They're hydrogen dominated, but they have massive amounts of methane in the atmosphere. And these numbers are essentially the temperature, which is a proxy for distance from the star. It doesn't matter where we put it. You have a lot of hydrocarbons in the mantle, they outgas methane, and the atmosphere becomes methane dominated. And if you have methane present in the atmosphere, you're parked next to a star, what you make is hazes. And so we put in a haze model, and we showed that the presence of hazes are likely, and it's really hard to turn the hazes off unless you add an awful lot of water. And so this is our predicted transmission spectrum. This is without hazes in the blue and with hazes in the sort of orange, yellow something. Okay, so hazes should be present, methane-rich atmospheres. Prediction 2, soot planets are in the existing inventory. So we did the same thing as Luke and Powell. We looked at the density of material if it was sort of a soot planet or a soot water world or a rocky planet. So that's what are shown here. So this is the radius versus mass. This is an Earth-like composition. The underlying data shows you the exoplanet mass and radius. Here's the soot planet. All right. This is the soot water world, and these ranges have to do with the fact that we don't know exactly the composition of the hydrocarbons, and we don't know exactly how it's going to behave, so we tried to account for that. And the soot water worlds are this dotted line, or the water worlds is this dotted line. So you see our saltwater world essentially overlaps the Luke and Powell number. And this shows you in the purple band, shows what if you add a hydrogen layer of 1% onto this rocky planet, what that would look like. So all these things are degenerate, and we have added another degeneracy to this question. All right, so when you look in this mass radius things, a 50-50 water world is degenerate with the soot planets, so we don't really know. But what we can tell you is that the solar system tells you that this carbon is there, right? So we think this is a more likely solution. One of these two different plots, uh, one of the other things that is all the rage in the exoplanet world these days is that the pressures are high enough for some of these sub-Neptunes that they may enter a phase what's called miscibility, where instead of having multiple layers, where essentially the Earth is layered compositionally, everything is mixed together. That is, the hydrogen seeks into the molten mantle, and so single layer, multi-layer, these planets are likely out there. And indeed, a paper by Lin and Seeger of one of these sub-Neptunes. This is the spectrum, transmission spectrum of probably K2-18b or TOI2 something or other. Uh, this shows methane in the atmosphere, that most of these bumps are methane, but also CO2. These two things don't want to be there together. And so one solution is that they're what is so-called Hycean worlds, that there's a water ocean underneath. That's Madhusudan and others are suggesting that. And Lin and Seeger said, well, no, if you account for the carbon content that is likely there, this could be essentially a soot-rich planet. Prediction three. If planets inside the soot line, if planets are forming such as the Earth inside the soot line, there should be products of carbon grain destruction in the gas. So we should look in the disk and we should see products of carbon grain destruction. And indeed, when we look around very low mass stars, that is stars below zero point 0.2 solar masses, James Webb is showing incredible complexity in the spectra. And the spectra have features of massive amounts of hydrocarbons. So that is, there is something that is generating a hydrocarbon-rich chemistry in these systems. Now, there is a problem with the soot line model in this construct, because if we go to solar mass stars, where the soot line should be further out and the products of carbon grain destruction should be more prevalent, instead, solar mass stars appear to be water dominated. And what you're looking at here are the spectra of solar mass stars from another paper, and you see all the blue there is essentially water vapor. So they're water dominated and not carbon dominated. So what's going on here? There's two different models that are currently accounting for this. One is carbon grain destruction, followed by outward diffusion of carbon-rich gas. And the other is that it's methane that's coming in from the outer disk, methane gas coming in from the outer disk at later times that is powering the carbon rich nature of these objects. And we can talk about how we think you can get around this solar mass problem. This is a ongoing area of research. I can give you one result that's hot off the presses from my student Maria Jose or Majo Colmenares. This is a class 1 source where we observe it in absorption. You can see the AMA image here. So this is the 1.3 millimeter. There's C18O showing the disk. This shows the what we think is the surface of the wind. How do we know that? Well, this is an H2 line, the S3 line. You can see the beautiful wind essentially coming from this source, and nickel 2, which I'd never seen before, shows a gorgeous jet. So this is a young source. We see carbon-rich gas in absorption in this thing. This is C2H2, where we have the P, Q, and R branches. It's just a gorgeous display of molecular astrophysics. And this is a young source that appears to be very carbon rich. So that can't be late supply of methane. And it's likely the destruction of carbon rich material, although, again, that's an area that is still being explored. So, to summarize, The to make a carbon poor Earth requires a separation of carbon poor inner solar system from a carbon rich outer solar system. Based on our understanding of the Earth, we have a reconception of planet composition in the inner disk. This is not the outer disk and the ices. This is the inner disk and the refractories. That is, soot-rich planets likely exist in the current inventory of exoplanets. These will be a natural source for haze production. For Earth-sized world, what does this mean for habitability? That is super fascinating. What about giant planets? As I told you, Uranus and Neptune have been reimagined. That's the Malamud paper. For planet formation, I believe we're detecting the products of carbon grain destruction, but I'm going to keep an open mind. And I haven't talked about it, but what's making this macromolecular material that is the material that makes it to the Earth and leads to the formation of life? It's likely that is actually related to pause that are now being detected directly in the dense ISM. Those pause are freezing onto grains and being provided to the disk. And it's likely we are now maybe going to be able to try to put together some of the pieces of the history of carbon, both at the early stages all the way to the planet stages. And there's an awful lot more work to do here, and just a lot of fun. And I'm happy to take your questions.
Great. Thank you very much, Ted. That's fantastic. So we have time, plenty of time for questions and discussion. Maybe we can try and organize by the topics. So solar system or Earth and solar system results you presented, then maybe the exoplanet, the demographics, and then the formation phases. On the solar system, does this model predict there will be different kinds of comets? Like some comets would be carbon rich and some comets, so as you have to remind me, is that the true then?
Oh
Um,
no. You know, one of the complications um,
you'd have comets
that
which are carbon rich and some comets would be, or is
right.
it
So
all
so
carbon rich?
th- there is there's a population of comets called sun grazers. Okay, and when these things get close to star, they get completely ablated.
Hmm.
All right. And for one of those comets, I was able to get a composition, and I published it in the original work. It's not on this plot, but it was in the 2015 paper. And that comet had chondritic level, CC level carbon content. Um, the comet community doesn't really pay attention to this stuff all that much, but I think they should. It's hard to do, but yes, there at least was one comet. Well, there were two sun grazers, but dynamically they might be the same comet. We don't know. One, maybe two comets that are carbon poor. Another complication is that Ryugu and Bennu are have CC-like composition. And so the idea is that they formed beyond Jupiter and then everything got flung into the asteroid belt.
Mhm.
And maybe that's true. A part of me says, how? And how does that work? It's obviously very complex, and Jupiter's, doing stuff with Saturn. There's the grand tack theory and lots of other stuff. So obviously it's complicated. But from the disk perspective, this is a complication that this stuff not has to be born here and then thrown over here.
Mhm. All right, and people online, of course, raise your hands if you have questions first on the solar system results, and maybe Ryan and Virginia can help you there. Right. In terms of the Earth's carbon content, how well known is it, and why is it so low then? What's the, because there's some, was it all delivered later, or was there some residual from
Right.
soot?
Okay. So the when in a silicon melt, when you were in an oxygen rich environment, i.e., when water and is running around, the carbon will partition with the iron, and by that's the geo term that I sort of think of it as sort of like reacts. And so it'll make iron carbides, and that then sinks to the core. All right. And so that's one statement. Okay. This number, what we did here, and this was in the 2021 paper, my colleague Jackie Lee looked at all the geophysical constraints, that is, the geochemical and the geophysical, the Alfvén wave propagation, the density, and so on and so forth, to come up with this bulk Earth number. Now we had a range here, and other people have done other work, and so the upper limit for the Earth is probably somewhere here. And we know there's a light element in the core, and carbon is a likely contributor to that. So then it brings up the question why, and this is one of the things I was thinking, why is there carbon on the surface in the first place at all? Right?
Mm.
And so does that mean that there's some later supply? And the answer to that presumably is yes. And there is this concept of what's something called the late veneer, where the Earth got all of its lovely stuff at some later time. That particular model seems to be going out of favor, but nonetheless, the Earth is getting material all the time, and some of that stuff has carbon, and it's coming presumably after the Earth solidified or partially solidified. Alternately, there could be, if it was a reducing environment, then the partitioning in the magma ocean happens a little bit differently.
So the carbon content of the Earth is dominated by what's in the core, but that's hard to measure, and you think
Yep,
it's an upper limit,
that's right.
basically.
It's
Okay.
100%. I mean, the light element in the core could be anything from hydrogen to silicon.
Hmm.
And we're astronomers. Silicon is not a light element, but there we go.
And in the moon, is there anything useful in the moon to for measurement in the moon? Or?
No, I mean it's made of the Earth's mantle.
Hmm. Right.
And no, I guess if you could figure out the carbon content and how the Earth, the moon, I mean the moon is carbon poor by and large, so it's made of the Earth's mantle. So I don't know if it gives you any useful information in this context.
Mhm. All right. Any other questions on solar system related to measure? We can always come back, of course, if people think about things. The exoplanet demographics that you showed, Luke and Pavel's result, would one expect a clustering in the, I mean, they sort of hinted at clustering here, but I guess you'd have to go under the radius valley, so get rid of your hydrogen, and then do you expect a clustering in the density properties?
Yeah, I this data is I mean I'm just struck by how well it matched, right? And when we look at it with current data, you know, it's the rocky planet. There's much more dispersion in the data that we took.
Mhm.
So I don't think you can say the radius and the masses, I don't think they're well enough determined. And there's so many degeneracies in these plots. Okay. And so what I would say is this is an educated degeneracy.
Mhm. Well, you'd need to remove, you need to be under the, so there's no hydrogen helium atmosphere. So under the radius valley, but then in there, there'd be
Yep.
worlds that are carbon poor and carbon
You
rich.
got you have carbon rich, and then the carbon rich planets, you just put a little hydrogen envelope on them and you push them up here. So right now the soot planets sort of lie kind of close to the radius valley in both of these solutions, but you put a hydrogen rich envelope and then they can be pushed up here.
Mhm. So Virginia, is there anybody there want to? You should probably unmute in case you want to shout out some questions. Um, I'm sure there are other things in the exoplanet statistics here that we could go to, but I know many people are working on the disks, so we could go to planet formation processes next.
I have a question on the planet formation side of
Please.
things. If I can, we can start that discussion now.
Yeah.
Hi, thanks for the presentation. Just a question about the last disk you showed, the class one. It looks like that disk doesn't have all those kind of additional hydrocarbons that are seen around the very low mass disk. So could that instead just mean that that methane gas gets resupplied later, and that could still be a possible explanation rather than carbon destruction because we don't see all those other features that we're seeing in the lower mass stars, or no?
Right. So it's an evolving field. And so you're going to get my perspective at this current moment. I'm not showing it here. We do detect methane,
Okay.
and we do detect, I think, one of the other hydrocarbons, but it's certainly not one of these massive hydrocarbon explosion sources. Okay.
Yeah.
In general, the other hydrocarbons, the more extensive hydrocarbons, are slightly lower in temperature than the C2H2 that is seen, right? So our concept is that you have some process destroying grains close to the star, carbon-rich material, all right? And then it diffuses outwards, and as it diffuses outward, it cools down, all right? And that's when these other hydrocarbons form, right? Now, in this source, this is really fascinating in that this material you're looking at here is moving. All right. It is actually, we're with Webb, we're able to show that it is about 40 to 50 kilometers per second off rest. And it's entrained, we think, in the base of a wind. This is also water rich. There's an awful lot of water in this material. There's a lot of methane, a lot of C2H2. But the chemistry of this object in terms of the hydrocarbons to CO ratio and the hydrocarbons to HCN ratio is very distinct. There's an awful lot of hydrocarbons relative to other stuff. And what we think is happening is that it's likely we're looking at it in absorption sort of, you know, we're catching something to do where you see all this hot H2 here. It's something to do with that, and it's being launched. So it must be something that's upwelling. It's not being exposed to UV because there's so much water there that the water would self-shield and protect the whole thing from radiation. So it's not radiation that is providing the carbon material. It has to come from somewhere. All right. And so the likelihood is still carbon grains. Doesn't mean that it couldn't have been something else, but there's not enough methane ice in the ISM to give you the carbon content we're seeing here. This would be about half of the available carbon based upon the amount of CO we see, although that is a not fully defined number. And that is, we have some CO observations from the ground, but we're missing some of the temperature components.
So maybe we can just generally discuss these spectra then. The carbon rich it's a dichotomy as far as I can see, right? So my understanding is so even the carbon rich ones have water, so there's some water there, but then there are some which just don't have the carbon or so much.
That's right.
Would you describe it as a dichotomy?
That's right. Well, I mean, the dichotomy is that when is the very low mass stars when we get to the class 2 population. So when you're below zero point 0.2 solar masses, they appear to be very hydrocarbon rich. There is water there. Whereas when we get above that, you are predominantly water rich, although there are exceptions. You know, Maho has another paper based upon ILSA's DECO program, that JWST DECO program. And we do see some carbon-rich disks in that sample, but it's still water dominated by and large. So what's going on there? Well, Maho in another paper discussed the fact that the source that we had a solar mass star that had carbon-rich material, and it had an accretion rate that was comparable to that of very low mass stars. That is, very low mass stars have very low accretion rates. The accretion rate scales is basically the stellar mass squared. And so our idea was, well, maybe it's related to that, is that if you have something happening in the midplane that's upwelling and you have a high accretion rate, it as it's upwelling, it gets pushed into the star. So for the solar mass stars, you might lose that material before you can get it to the surface where it's observable. And the very low mass stars, the accretion rates are low, you can have this outward diffusion as well. And Adrian Hogue wrote a paper with greater detail of this concept. And it seems to sort of kind of work, but it is complicated. There's an awful lot of stuff going on there. And so that's one idea. But the other idea, the Ma concept, where it becomes carbon rich with age, that paper is awesome. The Ma et al. 2022-2023 paper. It's really great. And I think there's some concepts of that that are in that paper that are important as well. Because very low mass, as you get to older systems, they do appear to be getting more carbon rich. And one idea that Ma came up with is that the water is lost early because the grains are drifting in, and so the disks become more progressively water poor, and maybe that's why they become carbon rich as you go later. And then it's just a question of where is that carbon coming from? There's two places, CO or refractory organics.
Right, but the refractory organics would be drifting as well, unless you're saying
100%. And at 100%. 100%. CC chondrates formed at about 2 million years. All right. So that says some stuff that was carbon rich, sort of, formed in the earth fairly late. And so it makes me wonder about late grain evolution in the class two systems.
Well, we can come back to I have more questions, but let's go to Arthur's question.
Thanks, Ted. This is a great talk. It was very easy to follow. I was just curious. So we were looking at this recent formation review paper. I'm trying to remember the lead author, but one thing that stuck out to us, it was maybe a simple question to ask is, in their plot, there's just have a simple plot of the elemental abundances in Uranus and Neptune, and you made it, pretty convincing point talking about Uranus and Neptune for the carbon. I also know that the sulfur abundances are similarly. Okay, you're laughing. Okay, so I was just, I thought, oh, maybe this is something that's been solved. I asked this very innocent question, but I guess ultimately what I'd be curious about is because they're both seemingly elevated to the same degree. Is there any way to say, people are interested for the directly imaged planets, looking at the sulfur abundances? Is this something, the direction we're headed, and putting this in context of what you described here?
It's good to see you, Arthur. The sulfur is also fascinating. So nominally, it is classified geochemically as a moderately volatile element. That is, its transition from the solid to the gas would be of order 700 to 800 K. So sort of comparable to what we are guesstimating for the refractory carbon content. And so the carbon and the sulfur should kind of track to each other. And we did look at that. And indeed, what we found, at least when we looked at the meteoritic inventory, is that carbon, sources that had 100% silicon had slightly less carbon and slightly less and even less water. So the sequence is that sulfur appears to be slightly more refractory than carbon, and carbon more refractory than water. Um, Use the term volatility. The problem we have from the interstellar perspective is that we can't see where the sulfur is. Uh, and with the carbon, we know that it's in this macromolecular material, probably, and it's in carbonaceous.
Right.
We know that half the carbon is in dust in the general ISM. With sulfur, we don't know where it is, but it appears to show up in spots where there's some disturbance. And so it suggests that it's in something that can come off, but not as easily. And so that's what makes it harder. But sulfur is another frontier to explore. If I were to think about it, I started my carbon journey 10 years ago. Someone should start on a sulfur journey, and I know there are people that are doing that. There's an awful lot that can be learned still.
I'm just following. We'll go to Virginia in a second, but just following up on that. How sharp do you think the soot line is? I mean, some carbon's in diamond, of course, or perhaps not much.
My gut. Okay, so I think that the material forming in dark clouds, so we're detecting pHs, individual pHs in a source like the Taurus molecular cloud one. It's a dark cloud, densities 10 to the fifth, temperature of 10K, no stars, and we're seeing pyrene, essentially. Well, we've detected cyanopyrene, which formed from pyrene, and pyrene is a four-ring PA. That's Gabby Wenzel led that effort along with Brett McGuire. And the McGuire group and Pepe Chernichero are detecting a whole bunch of hydrocarbons, complex hydrocarbons forming in that environment. That material doesn't want to stay in the gas, it goes on the grains. And then it gets to the disk, and those grains can move around. It gets exposed to radiation, but some of that material probably doesn't get exposed to as much radiation. And so some material makes this macromolecular stuff. Some of it is just probably pure pause. And so my gut says is that there's a distribution of material. Some stuff that's harder to lose, some stuff that's easier to lose. And what we're seeing is the stuff that's easier to lose. But that's all just waving my hands.
But most of it would be, I guess, for the Earth. You're saying most of it would be in the stuff that's easy to lose, and
Yep.
a large fraction.
Yep.
Question in Virginia, then, please.
Yeah, hi there. I was wondering what processes are you thinking of for grain destruction, if not sublimation?
Sure. And so we looked at photoablation and chemisputtering. So chemisputtering is essentially burning. So an oxygen atom can hit a carbon grain and it basically makes a CO if you're at about 500K and a high enough pressure. And so that would be a really easy way. I can get rid of the carbon grains, keep my silicates intact, everything's great. The problem you have is all the carbon grains are in the midplane, where the oxygen's in water. All right. And so you have to loft those grains up to height where the oxygen is. And we looked at it, paper Dana Anderson and also Zhongyuan Li, and we couldn't make that work. All right. Photoablation, where you bring up the small grains and break them apart. There was a recent paper, I forget the last name, where they were able to show that maybe that works. The problem is everything that we looked at where it might work is at like 1 AU, and Ryugu and Bennu are out at 5 AU, right? And there's nothing that works at 5 AU in terms of radiation. And so then you're left with sublimation or what's called pyrolysis, where it sort of breaks apart a little bit first and then starts releasing stuff. And so it is possible that photo effects are important, and maybe it's dominant since with Webb we're observing surfaces, right? Uh, but you have to, most of the carbons in deeper down, you have to bring it up.
Mhm.
Just to quickly follow up on that, could interstellar radiation work at 5 AU if it's strong enough in a cluster, or still not enough?
Well, you would say yes, but Javier Goicoechea, as you are well aware, has a paper where he looked at the carbon content and didn't
Yeah,
see anything
yeah.
special.
But let me try. I thought we were just thinking when they reach a certain temperature, the soot will come off. But are you talking about is it not just thermal evaporation or sublimation? Or
Right.
why do you need the radiation?
So when we first thought about this, we looked at the chemi sputtering because that was the obvious solution. And then, okay, so the way to do that is if you catch things when they're young, if the disks when they're young, before all the grains have evolved and you made pebbles. If I can destroy the small things first before I make the pebbles, then I've solved my problem. That was the idea. All
Mm.
right. And so that's why we looked at chemi sputtering. And well, if you're going to do chemi sputtering, you're up at a surface, you may as well look at photons. And there is laboratory work that shows that if you irradiate this carbonaceous material, this out of Emmanuel Detroit's group, a paper by Alata, and it can basically throw off methane molecules. And so there's some laboratory work that says that, hey, this is a way that actually works. All right. My problem is that the surface doesn't have much mass and all the grains are in the midplane. And so that's what drove us to a midplane solution, which is sublimation.
Hmm. Well, Henning was chatting about hydrogenation. I'm trying to remember now if
I think he was probably talking about dehydrogenation.
dehydrogenation. So what is that a different
I
mechanism?
assume it's hydrogen loss. I mean, if you heat these things up, the hydrogen's going to come off, or you expose it to radiation, the hydrogen comes off. Now, maybe there's some way if you add hydrogen to it, it makes it come apart. I don't know. I have no idea.
Uh-huh. He's on next week. We should try and ask him that next week. Okay. We're near the hour here. Any last questions in Virginia there or anywhere else? I had one last one, which is the temperature structure you showed in your disk at early times is higher because of higher accretion rates. Is your temperature structure set by
I can introduce themselves
accretional heating,
because they're welcome to stick around.
viscous local heating in the disk, or are you doing it from the start?
Yeah, it's the viscous heating. I have another plot that's a little bit better. And so this is an alpha disk with an alpha of 10 to the minus 2 or 10 to the minus 3. This line here, this is 10 to the minus 4. And some viscous heating, and this is stellar dominated. Same thing here. Alpha 10 to the minus 3, alpha 10 to the minus 4, stellar dominated. And this is where the planets are with respect to the various plots.
But viscous heating should dominate in the closer end, shouldn't it, in the midplane?
So, right. So none of this is general disk heating. You are correct that if we have some sort of accretion, and it would only be if the accretion was coming in the midplane, that maybe you would have a different structure, and that's not what we are modeling here. There is some work that's coming out of Melissa McClure's efforts, where she detected essentially the process of condensation, where things start hot, cool down, and you make minerals, essentially, when things are very young. And there you have this accretion dominated heating in the midplane. And maybe that's an important part of this carbon story as well, because condensation does not make organics. And condensation would lead to silicate-rich material and put the carbon in CO. So that's another solution for how you get a carbon-poor world.
Mm-hmm. Well, fascinating. Lots of questions are still to be answered here. So let's thank Ted again for a great talk and discussion.
Thanks, everybody. It's great to see